Often, instead of specifying the complex impedance of a load like we just did, we'll have no idea about the actual inductance, capacitance or reactance or resistance of the circuit. And instead, loads are described using the term that we brought up in the last lecture, power factor. In fact, power factor almost exclusively, unless you're buying new equipment, if you're a utility engineer, power factor is really probably the most ubiquitous method by which loads are specified in electric power systems. Since the impedance of a load is a complex number, it can be drawn as a vector in the imaginary plane, as we're showing here. And due to this complex nature, in general, a phase shift will exist between the voltage and the current waveforms. And there will be an angle, time angle, between them. And that same time angle that is represented here in the complex impedance plane and here in the voltage and current as a function of time graph also shows up in the power triangle between real and apparent power, right? In all of these cases, making the point, theta is the same. Right? Theta, same. Omega t, sorry, not omega t. Theta is the same. Theta, it's all the same. Power factor, as we said before, given PF, is by definition the cosine of theta, right? So that's usually how we'll calculate it. We'll use this cosine of theta. But I think it's more instructive to really rearrange this. What is the cosine of theta? Well, let's look at this power triangle here. The cosine of theta from SOHCAHTOA is adjacent over hypotenuse. Cosine of theta is equal to P over S. Right. So really what it is power factor is the ratio. I should point this out. This is the magnitudes of these, right? P doesn't have an angle on it. S does, so this is a magnitude. So most frequently, power factor, really what it should tell you, it's the ratio of real power to apparent power in a circuit. That's what power factor tells you. What is my ratio of real to apparent power? From this formulation, we can see that a low power factor is undesirable for utilities, as if this is low, that means there's a lot of reactive power that's oscillating through the lines in the equipment, right? Could have also, I guess, written this as P over the square root of P squared plus Q squared, right? And what that is showing us is that if power factor is low, that means there's a lot of Q in the circuit as compared to the P, right? So what's the problem with that? Well, when there's a lot of apparent power or a lot of reactive power, there's additional loss in heat, right? Why is that? Well, I have to supply the current. Current, even though this Q is not doing real work, it does draw real current. Now that current oscillates between energy being sourced into the reactive portion of the load and being delivered back to the source by the reactive portion of the load, but that current is still flowing back and forth, that extra current component. And there are resistive portions in the circuit that will produce Joule heating, and therefore energy loss. So owing to this property of kind of occupying lines with excess current and requiring higher equipment ratings per the kVA, reactive power is jokingly, maybe not jokingly, referred to as the cholesterol of the power system. So let's utilize this concept of power factor to describe a load. And this example would be one that would be very common in an industrial or utility setting. So we've got a vacuum cleaner. It draws 750 watts of real power at a voltage of 120 volts. And it is spec'd to be a power factor of 0.75 lagging. Very common style of description of a load in the power systems. You know, they didn't say anything about inductance and capacitance or resistance. They said what is its power draw and what's its power factor and is it leading or lagging. So what we want to know is what's the current draw, what's the reactive draw, and determine the impedance of the vacuum cleaner. So let's start. The first thing that we're going to do is we're going to determine the apparent power, and then we're going to use that to determine current. So we've got cosine of theta equals 0.75. And from our power triangle, we know that the magnitude of S is equal to the real power divided by the power factor. We were told that the real power was 750 watts, and here we've got the power factor of 0.75. And so that gives us a magnitude of apparent power. The magnitude of this angle is 1 kVA. Magnitude of this angle. The magnitude of this vector is 1 kVA. So we got 1 kilovolt for that magnitude. What we can do next is we can use that to determine the RMS current and the RMS voltage. So I know that the magnitude of the apparent power is just I RMS times V RMS. We said it was a 120 volt appliance, so we can solve for IRMS by dividing the magnitude of the apparent power by 120 volts. So we get IRMS is 1 kVA divided by that voltage, 120 volts RMS. And that gives us 8.33 amps. Okay. So we now know the current draw. It's 8.33 amps at 120 volts. We've got a couple different ways that we can determine the reactive power draw. How I'm going to choose to do it is that I'm going to use, I'm going to find out what the angle here is. Right? I know the magnitude of this, I know the magnitude of this. I can use that information to determine the angle. I actually know the relationship is 0.75, so theta is just the inverse cosine of 0.75. That gives us 41.4 degrees. And I can determine Q by multiplying S times the sine of theta. Just make some space. So that's at 1 kVA, sine of 41.4, and that's 661 var. Right. So now I've calculated current and reactive power. I can use the RMS voltage and the RMS current magnitudes to determine the magnitude of the impedance, which was the last part of the question. What is the impedance? So magnitude of the impedance is just magnitude of the voltage over magnitude of the current. All right, that's just Ohm's law rewritten, so it's 120 divided by 8.33. And so that gives me a impedance magnitude of 14.4 ohms. That's the magnitude of Z. Remember that the impedance triangle and the power triangle have to have the same angle. So if I want to kind of combine those two together, that's going to result in Z is equal to 14.4 at an angle of 41.4 degrees ohms, right? So I could just convert that over to rectangular form, and that would give me 10.8 ohms plus J 9.51 ohms. The 10.8 ohms plus J 9.51. We can look at that and we can say, okay, we've got a 10.8 ohm resistor in series with a 9.51 ohm inductor. That jives with our impedance angle, right? We have a positive impedance angle, meaning our impedance is in the first quadrant, as an inductive load should have. So if we wanted to write the voltage, well, we won't even do that. That wasn't part of the question, I guess. So we'll just leave it there. I think we've kind of covered it enough. The different power factors of individual loads will combine together into an aggregate power factor for the set of the loads that we aggregated. The calculation is going to be based directly on the combination of the impedances in series and parallel. So although mathematically it's a little complicated, qualitatively what we can kind of think of in our head is that if we have two loads that have different power factors and we connect them in parallel, their combined power factor is going to be somewhere in the middle of the two, and it will be closer to that of the larger magnitude load. Overall, utilities use this technique to try to maintain a system-wide power factor of between 1 and 0.8 lagging, with a kind of typical operational value being 0.9 lagging. So what utilities try to do is connect different loads together in parallel such that their aggregate power factor is about 0.9 lagging. When we're considering improvements that could be made to the power of a factor of a system, the first thing that we want to notice is that most loads that are actually out there look to be partially inductive rather than capacitive. And therefore, poor power factors lower than 0.9, are typically caused by large inductances in the load circuits, and not by capacitances. Therefore, the power factor in most circuits can be improved by compensating for the extra inductance by connecting a capacitor or bank of capacitors in parallel with the load. We're kind of showing that here. We've got a motor. We haven't looked at the circuit diagrams of motors officially yet, but we've talked about it enough in examples that you know that that motor looks like a resistor in series with an inductor, a very simple motor circuit model. And what we want to do is we want to cancel out the inductive reactance of this. What we do is we put in a capacitor in parallel with it. Why in parallel? Well, we could put it in series and they would directly add, right? That's kind of a novice circuit analysis technique. Let's just put that in series. What's the problem? Two major problems. If I put a circuit element in this branch, I affect the current draw of this branch. I also affect the voltage drop in the branch, and therefore I affect the real power that it's consuming. It's a big no-no. Number two is, from an operational standpoint, what would happen if this capacitor bank that we added to the circuit were to fail? If it's in series, if it was in series here, it would just disconnect us from the supply line. If it was in series here, it would disconnect us from the ground. In either way, a failure in the capacitor bank would cause the motor load to no longer operate. In parallel, if this capacitor bank were to fail, my power factor goes bad, but the motor still continues to operate, right? So the load would still run. So let's kind of look at this using the technique of the phasor diagram that we developed previously. The current here, I cap, is going to be given by the voltage across the capacitor divided by the impedance in the capacitor branch, which is just, in this circuit, the line to neutral voltage, divided by XC. Right? Voltage drop divided by the impedance. And remember that we can make a substitution where we could put in 1 over omega C here, right, for the capacitance, or for the capacitive reactance, and that's going to give us C omega V is the current, and that capacitance times omega times V. And this is going to, it's a capacitor, it's a pure capacitor, so the current here, I cap, is actually going to lead the voltage by 90 degrees. That current is also going to add to the inductive current, right? There's a little inductive current being pulled in by the motor here. And we can see this kind of, I think, best on the phasor diagram. So the first thing we're going to do is we're going to draw the original motor current. We've got the line, remember the line voltage, drawn here in black. That represents the voltage at the bus. We know that when we only consider the current draw of the motor load, it's going to be in the fourth quadrant because it's a resistive and inductive circuit. So we're just going to draw the current as some generic phasor in the fourth quadrant. The capacitor, if we recall, it's got a current flowing through it. It's got a magnitude of C omega V. Its phase has to be 90 degrees to the voltage across the capacitor, which is VLN in this case because it's in parallel. So this capacitor has to be I cap C omega V is at 90 degrees here. Right? So what we can do is we can use this tip to tail method, translate I cap down to I motor, right? Those two currents are adding, right? KCL, so this is an application of KCL as a vector diagram. They're adding at this point. I've got one. I add my second current. The line current here is, remember, equal to the addition of those two. Again, that's just KVL. And so we've got this line current phasor drawn there. I line is equal to the vector sum of I cap plus I motor. So i.e. we've taken the phasor summation of those currents. The result here is that the inductive load can produce the same real power with less total current draw from the source. This is going to reduce the kVA demand from the line and therefore the monthly charge of the utility bill for the customers who are subject to a kVA demand. The energy charge that's getting charged to the motor in kilowatt hours is going to remain the same, except maybe for a small reduction to reduced I squared R losses. So what this technique did for us is the current that would have been drawn by the capacitor, or I guess is drawn by the capacitor, cancels out with the current portion of the motor that is drawn by its reactance. Those two cancel out. That current no longer needs to flow in this line. It doesn't affect the real power draw whatsoever of the motor. So it's a great technique. Preserve the real power, cancel out the reactive power. This current here is therefore only due to the real power draw of the motor if this is perfectly canceling that out. We don't typically have that in the system. Like we said 0.9 or higher is kind of a nice power factor to have. But that's the idea of power factor correction. So now let's do an example of power factor correction. An activity that's often performed at industrial companies, largely because utilities penalize large companies for having low power factor. They actually charge them for having low power factor. So we've got a 100 kilowatt load located at the end of a several mile long 12 kilovolt distribution line. The lumped resistance of the line is 10 ohms and the power factor of the load is 0.8 lagging. You need to determine the apparent power drawn by the load, the reactive power supplied by the source to the load, the current delivered to the load, and the distribution line loss to the load. We also want to determine the reduction in line losses that would result if we performed power factor correction to go from 0.8 lagging to 0.9, that doesn't say lagging, but it should, to 0.9 lagging. So we're going to perform a power factor correction. So the first thing that we want to do is we want to determine the apparent power in the original load before power factor correction. So we've got apparent power. We're going to look at this as the ratio of P to power factor, right? So this is 100 kilowatts. That was the real power consumption spec of the load, 100 kilowatt load. And we're going to divide that by the power factor, which was spec'd at 0.8 uncorrected. So we divide 100 kilowatts by 0.8, we get 125 kVA. Okay. So our magnitude of our apparent power is at 125 kVA. We can determine the magnitude of the reactive power straight from this. We just know that Q is going to be the magnitude of S squared minus P squared. So that's 125 squared minus 100 squared, 75 kilovar. And so now we've got the kind of the power profile of the load, if you will. We know that it draws 100 kilowatts of real power. It also draws 75 kilovar of reactive power. If we look at those, we can determine that's 125 kVA of apparent power. What does that mean in terms of voltage and current? Well, what we've got here is we've got some sort of distribution system. It's got a, I believe it was 10 ohm. Let me look at this. Yeah, 10 ohm resistance associated with it. And it was a 12 kilovolt distribution line. So what that is saying is that the voltage at the end of the distribution line is 12 kilovolts. So what we can do is we can say the magnitude of S is equal to the magnitude of the current times the magnitude of the voltage. We can use that. So 125 kVA that's going to be equal to whatever the current draw is, I. That 12 kilovolts is spec'd in RMS, so this is an RMS current that we're going to be calculating, and that's times 12 kilovolts. And so that gives us a current draw of 10.4 amps RMS. .4 amps. So in this line flowing to this load, there's 10.4 amps. We can determine the joule heating due to the current flow through that as just I squared R, right? That's joule heating. The joule heating is going to be, remember, that's just real power consumption, so it's 10.4 amps times the resistance, which is 10 ohms. So we get 1.08 kilowatts of line loss due to that joule heating. All right, so what happens if we go ahead and we change that power factor to 0.9? Well, we just got to rerun some of the math. I'm going to go through it a little bit quicker. We got the magnitude of the apparent power is equal to P over the power factor. So that we don't want to change our real power consumption. It's 100 kilowatts over 0.9. That gives us 111 kVA. Notice the apparent power has dropped as compared to the 125 kVA that we calculated previously due to our improved power factor. We now we should expect that Q is going to go down. So Q is going to be the square root of 111 squared minus 100 squared. So we get that, and we get 54.4 kilovar. So we've got 54.4 kilovar, where previously we had 75 kilovar for that. So, you know, we've got a nice reduction in Q by improving the power factor. We can now use S and the distribution voltage to determine the current. That's going to be 111 divided by 111 kVA divided by the distribution voltage, which stays the same, 12 kilovolts. So 111 divided by 12 is 9.25 amps. So now in that distribution circuit, we've got 9.25 amps of current flowing as opposed to 10.4 amps of current like we had previously. That's going to reduce our joule heating. We take 9.25, we square it, we multiply by 10. Joule heating power equals 9.25 squared times 10. Right? And that's going to give us 0.856 kilowatts. That's an 8. So previously we had 1.08 kilowatts. Now we've got 0.856 kilowatts. So, you know, about 0.2 kilowatts real power reduction in terms of heat loss, right? In the resistive part of the transmission line there, in that transmission resistance. And remember how that was done is that we just were connecting a capacitor in parallel. And we'll talk a little bit about how to actually calculate this value of the capacitor. But first we just want to quantify what the effects of changing the power factor actually are. So really what we can say is that we see that the line losses, there really are real power losses, even though that they're due to reactive power flow, because they result in the physical heating of lines due to that current flow. Even if it is attributable to that reactive power consumption. So reactive power consumption can have real power losses due to current flow. Okay, so now we want to calculate the size of the reactor necessary to improve the power factor from some old value theta 1 to some new value theta 2, or power factor angle, I should say. Let's talk about that. And I use the term reactor because a lot of times in capacitive system or in power systems, a capacitor supplying reactive bars is called a reactor. So to conceptualize this, what we're going to do is we're going to draw these two power triangles, one without the capacitor and one with the addition of the capacitor, right? So this is our original system. This is our power factor corrected system. So let's make these observations. The real power in kilowatts is the same for both. If all we did was add a reactive element If all we do is add this reactive element, it can't have an effect on the real power draw. Right? There cannot be a change in real power if all we do is add a reactive element and that voltage remains unchanged. That's a key point. That voltage has to remain unchanged. But assuming that voltage is constant right there, addition of this element can't change P. Inductors and capacitors don't consume real power. So the real power in both cases is exactly the same. P old equals P new, right? What will change is the reactive power, right? Q old here is equal to P times the tangent of our old angle, power angle. So we say, I'm going to call it Q old. It's equal to P tan of theta 1. Right? And in this new system, where we've added this reactive power from a capacitor, we've reduced the theta here, and we get Q new, or Q2 I guess, is equal to, P's the same, in this case it's tan theta 2, right? Theta new. This difference right here, this difference between the reactive power is due only to the addition of this capacitor. We could say that QC is equal to Q1 minus Q2. Right? That little vector right there. So we can take these observations and we can do some substitution, and we would find a general formula is that the Q necessary for the capacitor is going to be equal to the real power times big quantity, the square root of 1 over the old power factor squared minus the square root of 1 over the new power factor squared power factor 2 squared, that quantity minus 1. So that is the value of capacitive reactance that we need using those inverse tangent relationships. We didn't demonstrate the math. It takes a little bit of time to get there that we don't have in this class, but that's the formula for determining the reactance, reactive power required of the necessary capacitor from going from one to the other. So let's go ahead and figure out the sizing of a capacitor necessary for power factor correction. We want to determine the capacitor rating, rated in kilovars, and then also in farads, to improve a load power factor from 0.7 lagging to 0.9 lagging for a 256.6 volt distribution point that's delivering 500 kilowatts of real power at 60 hertz. At 60 hertz. I don't know why that's capitalized, sorry. So how are we going to do this? Well, let's kind of trudge through it. For the old power factor, the reactive power is Q old is going to be given to us by P tan theta old. Right? Old just meaning before we do the power factor correction. So it was a 500 kilowatt load. We said that it was 0.7 power factor. So that's 500 tangent I'm just going to throw this in. Inverse cosine of 0.7, right? So inverse cosine of 0.7 is going to result in an angle. I'm taking a tangent of that angle. That gives us 511 kilobars. We got 511 kilobar. So we can also determine the new power required, that's Q new, is going to be, we said we're going to compensate to 0.9 lagging. So that's just going to be, remember, stays unchanged, 500 tan of inverse cosine of 0.9. And that means we're going to have a reduction down to 242 kilobars. Right. So the reactive power supplied by the capacitor is just the difference between these two. Right? If that's what we're doing in power factor correction, we're putting in a capacitor into the circuit to kind of make up some of this here. This is our new power, reactive power. That was our old power. The difference has to be Q cap. $511 minus 242. And that's 269 kilovar. That's what the capacitor has to supply. All right. So that's what we were asking of our capacitor. Clear my slide. So Q cap was 269 kilovar. Just to summarize that. All right, so how do I determine the capacitance then? Well, we just go to our formula for power. Remember, it's voltage squared over impedance. So for a purely resistive element, Q is just equal to V squared over X. We can make the substitution for a capacitor that X is 1 over omega C. And that leaves us with Q is equal to omega V squared C. Omega times V squared C. So what we can then say is that we could solve this for C, which is Q, divide both sides by omega V squared. So we get that 269 kilovar. I need to divide by the angular frequency of the power system. That's, remember, the frequency of the US power grid is 60 hertz. That means the angular frequency is 2 pi times 60 hertz, 120 pi. It's a lot of times written. That's 377 radians per second. 120 pi. Now I need to multiply by the voltage squared. Remember, the voltage was spec'd at 265.6. We square that. We end up getting 10.1 microfarads. So we need to, for power factor correction, we need to find ourselves a 10.1 microfarad capacitor, so relatively small value of capacitance, but it has to be rated for 265.6 volts RMS. So this is a power capacitor that we would need. And if we add that just in parallel to the circuit that we had at the connection point of the load, we would correct from 0.7 power factor to 0.6 power factor, or to 0.9 power factor, excuse me.